Welcome to APEC. It's March 20th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, we are proud to feature Benjamin Solomon, who will be presenting an in-depth review of his research into gravity modification, along with Ron Kita, who will discuss his research into modifying gravity using electrets. After that, we'll catch up with the latest research from the Falcon space team, and we'll be wrapping up the event with open discussion and ad hoc presentations. So just a couple of quick reminders. You can view conference replays, details, and speaker information on our website at altpropulsion.com. Please save your questions for the Q&A session after each presentation. Type your questions into chat during the presentation, and we'll go through them after each presenter finishes. Now, I'd like to introduce you to our first guest. Benjamin T. Solomon is a member of the Nuclear and Future Flight Propulsion Technical Committee of the American Institute of Aeronautics and Astronautics, and the founder of the Zotus One Foundation, researching interstellar propulsion physics and technologies. He has decades of experience researching gravity modification and breakthrough propulsion physics, and he will be presenting a three-part discussion of fundamental principles, experimental evidence, and device engineering for gravity modification. So, Benjamin, welcome to today's call. I'm going to ask you to unmute, sir.
Unmuted.
There we go.
Right. Thank you. Thank you for having me on this conference. Let me share my slide.
There we go.
Okay, the basics. This is part one, which is basically lays down the context for the work I've done. When you understand the basics I'm looking at, you understand the experimental evidence and then the engineering design principles. These are the 5 most important things that I've done, and there's a lot more underneath it. In a sense, you can say this is the tip of the iceberg. Here, G is equal to tau c squared is the first equation in 300 years that does not have mass in the equation for gravitational acceleration. And G, I showed that G, capital G, is not a constant, it's a coefficient of isotopic mass, and that has consequences in astronomy. And quantum theory does not ask the question how probabilities are implemented in nature. So what I've been able to do is propose that question and propose how it's done. As a result of that, I was able to propose an alternative to the Schrödinger wave function, which I've named the probabilistic wave function. And I've also shown that probabilities and randomness are 2 different phenomena. Everything I say in this presentation, the current status quo physics world will consider it sacrilege. But I'm not a person who puts a theory on a pedestal. And I look at the data. What is the data telling me, and why is it telling me that? Okay, right now I'm the founder of a fintech startup, SaaS credit risk. It's based on AIR models. AIR stands for asymmetric information resolution. It's a means of structuring the data and the information in a method that allows us to infer private information. So for a business, the private information you want to know is what is the quality of management, what is the environment of that strategy. For physics, you want to know what's going on in the data. What is the data not telling you that you have to put together a structure to find out what's happening? Okay, so to go all the way back, a lot of this discovery is not a linear process. It's a haphazard, leap forward, leap backwards process. And I'll explain a little bit more by example how this whole thing came about. So I'm presenting it in a linear sequence so that it's easier to understand, to get the message across. Data is basically zeros and ones. There's nothing else. A name can be data. If you don't know the person, a name is data. You might as well use the driver's license number to identify a person if you don't know that person. Information is when the data has an emotional association. For example, the name of a person whom you know has an emotional association to it. If you look at a report, hey, it's a great report or it's a horrible report, that sort of things. That's the difference between information and data. This is from my experience. Knowledge are in domains, and they include information and data, plus they have instructions on how to use the data. Mathematical models in physics are basically instructions on how to use observations. And then wisdom is basically knowing when and where to use a specific domain, knowledge domain. Okay, the client directive. It basically states, this is something I put forward about 5-10 years ago. It says that we need to be bold and explore what others have not, seek what others will not, and change what others dare not. Reason why I named it after the late Maurice Klein, Professor Maurice Klein of mathematics at CUNY, City University of New York, is that he was the only one that I had come across who was objective enough and had enough courage to state that mathematics has become so sophisticated that it today can be used to prove anything. These are my publications. I've compiled all my published papers into 3 books, and 80%, 90% of the stuff in the books can be found at this web link. It's the published papers, so you don't need to buy the books to read what I've written. So what is gravity modification? It is the ability to modify velocity or acceleration without recourse to Newton's third law of motion. So that tells us 2 things. Propellantless propulsion is not necessarily gravity modification. And secondly, since we are trying to modify a field, what we need is something that can modify the field. Why cannot general relativity deliver gravity modification? Because it was written 100 years ago, and the thinking at that time was mass was the only thing that could modify gravity or alter space-time so that gravity is changed. So we have to understand that a lot of the stuff that we are dealing with has its origins between 100 to 300 years ago, and they need to be updated. So how do we modify gravity? We replace the mass source with a technology. And I have this egg shape here because I'll show it in a minute that that's how gravity changes the shape of particles. Okay, the next section is analysis is a double-edged sword. So we need to know how our methods of analysis affect our observations. The 2 major types of analysis is theory building is aggregation versus deconstruction. Aggregation happens when you have a simple theory, and then researchers add some more on top of that, and on top of that, and on top of that, until it becomes a big, complicated theory. Fundamentally, this process assumes that what was done earlier is correct. Whereas I use deconstruction. I take an observation and I break it down into simpler and simpler parts. And that's how I was able to make all the inferences and discoveries that I've done. Okay, another important consideration is falsifiability. And this was proposed by Karl Popper more than 100 years ago. But it requires, for falsifiability to be correct, it requires theory A and theory B to overlap. Then you can look at which part of which theory is correct and which part of which theory is not correct. And it's a very powerful tool. You'll see an example of that in a minute, in part 3. And so general relativity and quantum theory are not falsifiable. They do not falsify each other because they operate in completely different domains, knowledge domains. Context versus focus. So are we looking at the field, or are we looking at the field phenomena, which is acceleration? Contexts may be logically associated with each other. For example, if you want to study what's happening inside the sun or a black hole, you use quantum theory to study the processes, but you use general relativity, so to speak, to understand how gravity is altering those processes. And then contexts can be nested: where, who, what, when. For example, if you look at this picture, you can see that this photograph was taken probably in a European college town, not an American college town, late summer or late spring or early fall. And then when you look at the context, within that outer context is who's this person. She's educated. She's probably above average intelligence, not very materialistic, probably health conscious. And you can see a few, that sort of things. If I could see what her face is, I have an eye model that can translate the body features and facial features into personalities at birth. But here I cannot see what her features are, so I cannot tell that. And then the innermost context is what's she doing? She's looking at some store behind us, and she's focusing on what the VR technology is telling her about that store. And you can tell that by her stance. So you can tell a lot of things. If you know how to read the data, the information, you can tell a lot of things. And if some of it may be guesses, what you need to do is take those guesses and go back and verify. Okay, now you see this dancer. It was invented by Nobuyuki Kayahara. And some of you will see her rotating anti-clockwise, some of you will see her rotating clockwise. And if you look at her feet, you'll see it's moving up and down. She's moving up and down. But it's a still. It's a series of still. So it shows you the power of the brain to overlay motion on a picture, because the brain has algorithms to decode visual content and audio content. So we have to be careful about whether we are seeing what we know or whether we know what we are seeing. Knowing what you see requires a process of discovery. Seeing what you know does not. So there are those two very important distinctions we have to make when we're doing the process of discovery. Okay. I believe in 1958, Roger Penrose proposed that particles, when they fall in a gravitational field, they elongate. And so this guy, in 1968, about 10 years later, Gabriel Veneziano he proposed string theories, which are basically particles that expand and increase their frequency as they get more energy. So you could say that Roger Penrose is the spiritual father of string theories, whereas Gabriel Veneziano is the father of string theories. But string theory, politics, and all the rest of it is a lot more complicated. If you read up on it, you'll find that somebody else is considered the father of string theory. But it's all irrelevant, because if you require that Lorentz-Fitzgerald transformation, this, and Newtonian gravitational transformation are evident, they both say that particles contract in the direction of travel. And so how do you explain this elongation? While particles contract, their distances between particles increases. And so that's why macro objects appear to elongate, do elongate, because the gravitational acceleration increases as you head towards the gravitational source, versus the particles that obey these transformation need to contract. So the one thing I have to point out here is that if you notice that for space, the reference distance is in the numerator. For time, the reference distance is in the denominator. And the same is true for nonlinear motion, which is the Newtonian. I gave it the name Newtonian because nobody else had given it the name. I found this on a St. Andrews website. I was hunting it high and low for what was going on in a gravitational field, and I found this in our St. Andrews website. St. Andrews is a university in the UK. So the question is, what's wrong with this visualization, with this illustration? There is a property of mass that people generally tend to ignore, and I do not know why. When the mass forms a circular structure like this, outside of the mass here, you can use general relativity or other Newtonian to model gravity as 1/r². But inside the mass, what happens is that the gravitational acceleration is at its peak at the edge, the surface, and as you go towards the center, it goes to zero. At the center, it is zero. So that is the spherical property of the gravitational field. And therefore, for this illustration to be correct, what we should see alongside these edges, we should see this structure coming up, forming a mound and not a hollow. And that's the reason why singularity doesn't exist in black holes. But that's another topic altogether. Then McClandish put forward this illustration of an alien recovery, is it recovery? Reproduction vehicle. And this is something I would like to talk about, but we all have to be on the same page. So for another session. So when you look at the context of an equation, each theory has a set of axioms. And some of the axioms are explicit. They are written down on the paper. This is the axiom that I'm using. Some of the axioms are implicit. Because we are so used to thinking about it, it becomes common sense. We don't write it down. And so when you look at an equation, you have to ask, what is the axioms behind this equation? Why do these axioms exist? And the context structure of that equation or set of equations are basically driven by the axioms. And so when we observe something, when we observe data, we have to derive at least one equation to have some semblance of objectivity. And we won't know until we do a lot more research that it is that it is really what's happening in nature. The next point is that fit. If you have the correct context structure, then we can plug in different concepts within that context structure, and they fit in with each other very nicely. So you have now a series of equations that work cooperatively with each other in that context structure. And therefore, we can explain why Occam's razor is true, is correct. Because as the theory gets more and more complicated, people add more implicit and explicit axioms, and then they say, oh, I need a theorem from that field. I bring that theorem in, and therefore we are importing axioms. By importing a theorem, we are importing additional axioms into the body of work we are working on. And so eventually we get lots of axioms, and most of them we are not aware of because we don't fully understand the axioms that we have imported from other pieces of work. So the scope of the validity of the body of work we're working on decreases. The more axioms you have, the smaller the scope of the validity of the theory. But paradoxically, the theory looks more general and more applicable. But you break one axiom and the theory is gone. Another piece is when you are analyzing data is consistency versus segmentation. So you see the electromagnetic spectrum, humans have divided it into X-rays, UV light, infrared, microwave, and all the various versions of radio waves. What I've shown that all photons are the same. And because all photons are the same, there is an opportunity for over-unity. But be careful. I've also shown that nature is exactingly definite about the conservation of mass energy. You cannot get free energy out of nothing if you don't understand what you're doing. In 2018, I talked to Susan Manwick in London. She runs an organization that has pulled in people to test their over-unity inventions, and not a single one of them has worked. That's because nature is very exacting about conservation of mass energy. But there is a way, in a later session, I will explain to you, because all photons are the same, there's a way of converting and getting more energy out of a photon than is actually visible. So let's go to the next part, which is deconstructing gravity. It's based on 20 years of work digging through the foundations of physics. Okay, what's with space-time? So here I present a 5-particle box paradox. Particle A, B, C, D, and there's a particle E that is coming in to the box at a certain velocity. So A, B, C, D are at rest with respect to each other, but not with respect to E. So what you find here is that the distance, measured distance AD, is different from the measured distance AE, even though particle D and particle A are the same location. So we know from this, we know that space-time is invariant. What is not invariant is the ruler by which we measure space-time. You can make this a 3-particle C, D, and E as an example, or you can make it as a cube for 8 particles forming a cube, and then particle E, you can measure the distance, the diagonal distance, but the same property holds, but people prefer something a little bit more complicated before they believe the results than something simple. So I stay with the 5-particle box paradox. And then we talked about ruler versus measure. We talked about Lorentz-Fitzgerald transformation and the Newtonian gravitational transformation. And we looked at why the reference statistic is on the numerator in one and the denominator is one. And this took me, even though I had discovered G is equal to tau c squared in 2007, it took me till 2017 or 18 before I finally figured this out. So it tells you that discovery is not a linear process. And the reason why that is the case, why one is the numerator, the other is the denominator, is when we're using it as a ruler, we're looking at the interval between two tick marks. And so you have, I got to see this. I don't bother to remember a lot of things. I record things so that I know what's going on. Yeah. So we have, just give me a second. Problem with being both short-sighted and long-sighted is neither short-sighted nor long-sighted. You cannot see things quite clearly as you need to see it. Okay, so as a ruler, you find that the environment that you're measuring is in the numerator and the reference is in the denominator. But when you're looking at actual measurements, like say the distance, you're actually counting the tick marks, number of tick marks in your observation. So you find that the opposite is true. The numerator is your reference and the denominator is your environment you're measuring. And so that explains why the distance looks different from time. It's actually the same. It's all the same. It's how we have interpreted it. So we get a function that looks like this. I believe that electric and magnetic fields are dimensions, but that's another story. Okay, we'll get to why do I put these two together? This is linear motion. This is nonlinear motion. Okay, so if you take a point, let's say particles falling in free fall, and the velocity at this point is v, and what happens is that's by linear motion, by nonlinear motion. What happens that is if you take this velocity at this point and convert it into the transformation, and then take that transformation and plug it back into the gravitational formula, or the other way around, plug it back into the linear motion, we find identical numbers. This is not something you can prove, you can discover analytically. You have to build numerical models and compare. And I'll show the results in part 2. So, so that's why the transformations are equal, if not equivalent, if not equal. So basically reinforcing that there's a consistency in nature. Nature does not say, this is linear motion. So hold on, let's talk about linear motion. And then on this side, no. This is nonlinear motion, and therefore we use nonlinear functions. No, nature doesn't care. They are both the same. There's something underlying it that makes both the same. You can solve the equations interchangeably. So how did I discover G is equal to tau c squared? I put forward a 3-step schema, and I'll use this again and again in other parts of my work. And this is part of the deconstruction I was using. So I broke up the gravitational field into 3 parts: the source, which according to physics from 100 years ago, it's basically mass, the field, which is the container, and the effect, which is G is equal to tau C squared. And so we have a three-part problem. We have deconstructed the problem into 3 parts. And so we are working with much simpler problems. And so when you look at a particle in the gravitational field at infinity, let's assume it's perfectly spherical, and the center of mass is here at the center of the sphere. Under gravitational field, a particle will experience nonlinear transformations. It's weaker on the far side and it's stronger on the near side of the gravitational field, gravitational source. And so you get nonlinear deformation. It's a deformed ovoid-like structure. And that deformation causes the center of mass of the particle to shift closer towards the gravitational source, and we see it as acceleration. And therefore, G is equal to tau C squared is derived from empirical data modeling. The second part of the interpretation of G is equal to tau C squared, we have H1 up here, which has its corresponding transformation lambda, and H2 down here, the height H2 down here, which has its corresponding transformation down here. The difference delta H is H1 minus H2, and the change in the transformation lambda H1 minus lambda H2 divided by H1 minus H2 is tau. Very simple. So you have a height, the transformation at here, minus the transformation up here, divided by that distance, multiplied by c squared. And you see, since the transformation has no units, you get acceleration meters per second squared. So acceleration is actually a spatial property. Even though we use time to calculate acceleration, it's actually a spatial property. Acceleration at this location is one thing, acceleration down here is something else. Even in a nonlinear motion, when you start accelerating, the velocity is one value, and you keep accelerating, the acceleration or the velocity at a different point is a different value. So there's a space and a time relationship or equivalence between the two. I chose to focus on the spatial side. Okay, so when we have a spatial gradient, like we have in gravitational fields, where V1 is less than V2 is less than V3 is less than V4, this is the spatial gradient of velocities. We have an acceleration that is orthogonal to the velocity gradient, to the velocity, and in the direction of the great increasing velocities. And I've shown that it is, this knife field is correct for gravitational, electromagnetic, and mechanical forces. So the next question we have to look at is it mass or matter? I believe, and I proposed a model, that it is not mass that causes gravitational fields, it is matter that causes gravitational fields. Mass is just a measure of the quantity of matter. And because of that, I was able to show that G, capital G, is not a constant, it's a coefficient, Gi, that is related to the isotopic mass of that specific element in this manner. It's hyperbolic, where K, ISO for isotope, is this value 2.573 something times 10 to the minus 6. So that has important implications for astronomy, because if you're using motion to determine the mass of an object, you're actually determining the composite GM of that planet or star. You have to use spectral analysis to determine the composition of the star, and then convert it back using GIMI is equal to KISO to get the mass of the planet or the star. Okay, Dr. Beckwith, he is my friend and colleague. Some of you know him from SPECIF 2009, 10, 11. He said that the problem with LQBS warp drive theory, even though it's based on GR, general relativity, is that even though the theory is based on a single universe, its axioms are based on a multiverse. And so the theoretical analysis, even though it is valid in itself, it produces nonsensical results. If you want to know more about why he said that, I would suggest you contact him. But the lesson here is that just because somebody says that their theory is based on GR, that doesn't mean it's correct. Because you can do a lot of things. You can add a lot of axioms, make it nice and spicy, and then say, hey, my theory is based on general relativity, therefore it's correct. No, general relativity does not give your theory some approval or pedigree that it is correct. No, it's independent by itself. It's very clear that it is substantially correct. But adding to it does not mean that your theory is going to be also substantially correct. So what about quantum theory? So quantum theory, particles are in space-time. And the reason why gravity passes through all particles is because the transformations present in space-time, whether they're Lorentz, Fitzgerald, or Newtonian gravitational transformations, are mirrored exactly on a particle. And that's why the particle deforms and we can get G is equal to tau c squared. And therefore, particles are a proxy of what's happening in space-time. So another thing we have to be aware of is Professor Nemerov of Minnesota University. He used NASA's Fermi Gamma Ray Space Telescope, and he found photographs where 3 photons that were 2 milliseconds apart, they arrived from a supernova gamma ray burst from 7 billion light years away. For them to travel 7 billion light years and come to Earth within 2 milliseconds of each other shows that space is empty. There's no such thing as quantum foam. There's no such thing as zero-point energy. People disagree with it. One of the people who disagreed with him said, "I'm going to recalculate quantum theory to show that foam is actually smaller than that." Go ahead. We live in a free country. We live in a free world. You can choose how you want to do what you want to do. So some additional thoughts to enlarging the context. Emergence. I think emergence is a very important concept, set of concepts to take into consideration, especially when we are developing theories in physics. Neither general relativity nor quantum theories are emergence compliant. So how do you look at emergence? Synergy is where the whole is greater than the sum of the parts. In emergence, the whole is different from the sum of the parts. So take, for example, the brain. The mind emerges from the brain. The brain by itself cannot really do anything. A dead brain is a dead brain because the mind ceases to exist. And so the mind emerges from the brain and does a whole lot of things. And then you can show, and I've shown this, you can show that a lot of properties in nature are actually emergent. And so, for example, the new property basically says that what emerges is different from what was previously there. And there's a way of analyzing and putting it all together. There are 7 other properties, but this is not the forum for it. maybe another session. So some thoughts on quantization. This is about 10, 15 years into my research, and I finally, it suddenly occurred to me, hey, space is vacuum. When you look at gravitational red and blue ships, they are analog. How do you explain quantization when you have this analog behavior of photons? So the only explanation is photons are quantized in the electron shell, or the equivalent, that's the nucleus. But otherwise, photons are analog structures. So that's something to think about when you're doing your research. And something else, which is, this is where I'm leaning. I haven't proven that this is exactly correct. This is mathematically robust. It's where my thinking is heading. The current accepted norm for dimensions are that it's simpler, it cannot be subdivided into simpler components, and it is quantifiable. But I would add two more things. Dimensions obey Lorentz Fitzgerald transformation and Newtonian gravitational transformations. If they don't obey it, they are not dimensions. And I believe I'm leaning towards electric and magnetic fields are fundamentally dimensions. And dimensions are scalar, but they undergo an emergence process that vectorizes the dimensions. You'll see that in a minute. So this is the shape of the universe that Einstein had suggested about 100 years ago. It's a shell, a spherical shell, expanding shell that's a sphere. And you have, with that shell, then you can say quite a few things, like the shell thickness is really a reflection of temporal reversibility. That means a process, that a particle can time reverse its behavior and go backwards. That's temporal reversibility, which is different from time travel. I suspect, and I cannot prove this yet, I think nobody can prove this yet, but it's something well worth thinking about, is that the thickness of that shell of the universe can be measured by the amount of temporal reversibility we can observe. And then the space vectorization is basically due to the expansion of the surface causes vectors to appear, to come forth, to provide dimensions X, Y, and Z. And similarly, the radial increase, the sphere expanding radially causes time to vectorize, and you get the arrow of time. So as far as we know, there's nothing inside and there's nothing outside. So so you see, in a context, we can now add a lot of concepts that are different, but they fit in together better than what we have seen so far. Okay, summary. I've talked about knife fields and how tau c squared is implemented knife fields, and that space-time is actually invariant, but it's the rulers that are changing. The gravitational constant, I'll get into it a little bit more, is not a constant, it's a coefficient. And particles, the reason why quantum theory is so successful, because it mimics the properties of space-time. The particle properties are in space-time and not in the particle itself. And I've proposed a few ideas for people to go off and think about and see whether they can develop new theories that give us new ways of looking at the world around us. Okay, that is the end of part 1. Let me get part 2 up and running.